Welcome back, everyone. This is lecture number 9. Page 1. We are moving from Italian mathematics of 1500s to 1600s, 17th century, which is known in history of mathematics as a truly heroic century. So, a heroic century obviously calls for its heroes, and at the time, some of the names must be mentioned here. Vieta, Napier, Descartes, Pascal, and Fermat were some of the most brilliant minds of French mathematics at the time. But today we are not going to talk in details about them, but we are going to talk rather about some mathematical gems from Isaac Newton. He was born in England and in 1642, and he is known for many great results and mathematical achievements. But today we'll talk about a very tiny fraction that has to do with binomial theorem. He discovered rather a formula for binomial expansion. He did not prove the formula, but he discovered the rule for it, or the formula rather. And we will talk about finding areas under the certain curves or under curves in general by the method of inverse of fluxions, which is in today's terms integration, or finding area under a curve by integrals. Okay, so one of the first Newton's great mathematical discoveries was that of the generalized binomial theorem. What is binomial theorem? This is part 1, by the way. There will be 3 parts to this lecture. So this is part 1. So we'll be talking about the binomial theorem and some of the series of Isaac Newton. So what is binomial theorem? It tells you how to expand expressions like a plus b to the power n. Alright, well, we know that he made a discovery about this formula, but it's not like formula was not known a little bit before him, but this is equal to, as if you remembered, but I'm writing it out anyway, a to the n plus n times a to the power n minus 1 times b plus n times n minus 1 over 2 factorial times a to the power n minus 2 times b to the 2 plus n times n minus 1 times n minus 2 over 3 factorial times a to the n minus 3 times b to the 3 and so on, all the way to b to the n. In fact, you can, these by the way are known as binomial coefficients. There is a formula for those, an expression for those. For example, 1 plus x to, let's say, some power r, you can write that in terms of the formula as follows. Here's how you write this. So you're taking the summation, if you have seen this before, let's say from 0 to infinity of r k x to the k, and that is equal to 1 plus rx plus r times r minus 1 over 2 factorial x to the 2 and so on, where this r choose k sometimes is known as r choose k, or the formula for binomial expression, coefficient is r, this is an r, times r minus 1 times r minus 2 times r minus k plus 1, the whole thing over k factorial. Okay, so that's another way of writing this. Okay, so as I said before, one of the first great mathematical discoveries was the generalized version of binomial formula, together with the rule for finding areas under a curve. Both and the rule for finding, so this is one, for finding areas under a curve. Under a curve. So both of this, I'll write what the rule is. I mean, you know the rule from calculus too, but I'll write the rule anyway. And both of this appeared in his of analysis, or De Analysis book, in 1669. So the rule says the following, and I'll draw the picture here. Let the base AB of any curve AD, have BD for its perpendicular. Okay. We call AB equals to x, BD equals to y, and let little a, little b, little c, etc. be some given quantities. Okay. And let m and n be some natural numbers. Then if a little a, which is some given quantity, times x to the power m over n, this is a rational power of x, is equal to y. So if this is true, it shall be that a times n over m plus n times x to the power m plus n over little n would be equal to area ABD. Let me just draw a picture here. This is nothing other than the power rule for an integral. So you'll recognize that from calculus 2, as I said before. So let's say if you have some curve AD. So let's say I have some curve. Let me call this curve AD. Okay. And I'm letting the base I'm calling that a perpendicular. This is D, this is B. Perpendicular, so let the base AB be that of any curve AD, and BD being the perpendicular. So we will call AB X, we will call B dy, and A, B, and C are some given quantities, and M and N are natural numbers, so we can talk about a rational power of x here. Then, if y is equal to a times x to the power m over n, then the area under this curve, is exactly equal to this quantity. Okay, so using this result, combined with binomial expansions which were known, Newton wrote down some progressions of expressions which calculated the area under curves, in particular families of curves. For example, he considered the following. So areas under families of curves. By the way, this discussion will be quite different from the one that is given in the book, as I will be talking about I'll be talking about his interpolation method for finding areas under families of certain curves and of curves in general. So pay attention to this lecture, as is not exactly as it is in the book. Okay, so he was interested in, so he considered, let me see. By the way, as I said before, both of these results appeared in the analysis. And I think he wrote the book in 1669. Okay, so now that with these two results, he'll use these results to actually explore areas under certain families of curves. So Newton considered, considered the areas under the curve 1 plus x. So what do I mean by areas under the curve 1 plus x? Each power, even the negative ones of this particular function, will give you a different function that will look very, very different from the previous one. For example, 1 plus x, when you draw the graph of that, it's a straight line. 1 plus x to the 2, it's a parabola. 1 plus x to the 3 also looks like a parabola. 1 plus x to the power 0 is just 1 and it's just a straight line. 1 plus x to the power minus 1, it'll look like a hyperbola. And he was interested in hyperbola. So here we are going to talk about various areas of under the curves, where the curves are different integer powers of 1 plus x. Okay, so with positive and negative powers. And negative powers. Okay. With other words, he considered the series of curves. The series of the following curves. Okay, well, so what would be y equals to 1 plus x to the power minus 1? this is the same as writing 1 over 1 plus x. And the graph of this looks like a parabola. Y equals to 1 plus x to the power 0 is just the line y equal to 1. It's a straight line. But the curve 1 plus x to the power 1 is just a straight line passing through the origin. I will draw the line in a bit. And then the line, well, not the line, but the curve 1 plus x to the power 2 is a parabola. 1 plus x to the power 3 also looks like a parabola, but a little bit more flattened towards the origin. Y 1 plus, well, this is not a parabola, but certainly not a parabola, but 1 plus x to the power 4 looks like a parabola, but flattened towards the origin. This has a different look, but I'll draw this in a moment. Okay, so since he was particularly interested in the hyperbola, he wanted to find an area expression by interpolation after having failed to obtain the area of under a parabola by purely geometric means. Okay, again, I repeat, known that at this time the expansion for something of the form a plus b to the n was known. So let me just draw the graphs for these curves, so it's clear from the picture what we're looking for. Okay. 1 over 1 plus x looks like a hyperbola, but a hyperbola, it has two parts. So I'm just going to consider the curves on the first paragraph. And it's a line, it's a line that looks like this. And it has another part. It has another part this way, but I'm not interested in that. Okay, so here we have 1, and here we also have 1. And let's see, what about the line or the curve 1 plus x to the power 0? This is just y equals to 1. So that is this line. That is this line. Okay. So this is the graph of y equals to 1 over 1 plus x. This is the graph of y equal to 1. The graph of 1 plus x to the power 1 is actually a straight line passing through the origin. This is the line y equals to 1 plus x. Okay, 1 plus x to the 2, it's a parabola, but shifted a little bit. But part of it is, let me see. So this is y equals to 1 plus x to the 2 to the power 2. And I should have drawn this a little bit more this way, but it doesn't matter. Let's say that this is the parabola. Okay, and y equals to 1 plus x to the third. It looks a little different, but we can still draw it here. It's not so important for what I'm about to say, but for those of you who don't remember what 1 over 1 plus x to the third looks like, it's some transformation of the following graph. That's x to the third. That's the general graph of x to the third, but since you have a 1 plus that, plus x inside the parentheses here, it'll be a shift. So again, we were going to consider that part of the curve that lies somewhere here, but for our purposes, there is enough lines or enough curves on the first paragraph, on the first quadrant, not paragraph, that we are going to consider. All right, so let me just mark a couple of things. All right, so let's see. Let me call this point here, point A. Okay. Okay, so this is little a. Let me call this point here little d. Let me call this point here little c. This is k. I am going to call, let me consider, I'm drawing this other line here. I'm calling this E, I'm calling this point B, I'm calling this point F, and I'm calling this point G, and I'm calling this point H. Okay, so now note the following. So here CD is equal to CK is equal to 1. I just said that before. I'm calling DE, I don't know what DE, but let me call that X. DE is equal to X. What is the line EB? This quantity B, EB, is actually the value of E, the value of E at what function? At the function 1 over 1 plus x. So if you were to substitute this E in for x in this quantity, you will get your B. So your EB here is nothing other than the value of the function 1 over 1 plus x at point E. So what would be EF? EF is nothing other than the value of E, the value of the function y equal to 1 at E, which is what? It's still 1. And EG, well, you have the 1 plus x here, so it will be the value of the function 1 plus x at the point E. And EH is the value of the function 1 plus x squared at E. So 1 plus x squared at E. So EG, EH, EF, EB, and so on, CD, are those y values in general that we're talking about. All right, so next, using his result, he calculated the areas under the curves over the segment DE, which is equal to X. So what we are going to do, so we're calculating now, calculating areas under the curve, well, under the curves, over the segment DE. That's what we're interested in. Over the segment DE equals to X. So probably I should just color code it a little bit. So let me mark this part with green. Let me mark under F with red. Okay. And let me mark with the G with blue. And since I'm running out of colors, I will do the other line also green. Okay, so this would be the first area that we'll consider under the curve y equal to 1 over 1 plus x from D to E, meaning over the segment DE, which is equal to x. Then we are going to calculate the area of the curve y equal to 1 over the segment DE, so that would be this other rectangle. Then we are going to calculate the area under 1 plus x over the segment DE, so it will be the area under the blue line from D to E. And then area under the curve 1 plus x to the 2, meaning area under this green line again from D to E. And as I said before, Newton is going to use his result for that. So let me see what I have and why is that so. So let's see. Area. The first area that we'll talk about is area AFDE. Keep in mind, I'm starting with AFDE because ultimately he was interested in areas under the hyperbolas. So we are going to find out under the red, under this blue, under this green, and then we are going to tabulate the results and looking for a pattern to say something about the area under this first green line over the segment DE. That's the plan actually. Okay, so area AFCD, not CD but DE is, so area AFDE, that's a rectangle. The rectangle has the length of the base x and the height 1. So 1 times x is just x. All right. Now area of AGED. Area of AGDE, meaning area under the blue line. So again, I have some sort of quadrilateral there. Looks like a trapezoid, but nonetheless, so using this rule, which is the integral, or the power rule for the integral here, the area under the blue line would be the area under the curve 1 plus x from D to E. So using this result, let's see. Um, your y for this part, your y is 1 plus x. Okay, then you use the power rule here for absolutely each term. So with other words, that's the same as saying what would be the integral of 1. The integral of 1, as you hopefully all know, is just x. And again, using the power rule, the integral of x would be x to the 2 over 2. x to the 2 over 2. So x to the 2 over 2, meaning whatever the power of this is, you add 1 to it and you divide by that power. So x to the power 1, 1 plus 1 is 2, so you'll have x to the 2 over 2. I'm just reminding you once again of this rule. So this would be this area. Area, let's see, AHED, ED, so that's the area under this other upper green line from, or green curve from D to E. So area AHED, that would be equal to the area 1 plus x squared under this curve from D to E. So this is the same as area 1 plus x squared is 1 plus 2x plus x squared. And according again to this rule, you take the integral of each of this. So the integral of 1 is x. Integral of 2x is, you leave the 2 alone. And x to the power, this is x to the power 1. So you have x to the power 1 plus 1 over 2. So 2 times x to the 2 over 2. And this is x to the 3 over 3. So that's the area under this other green line. So let me just write here rule number 2 that appeared in the analysis. I'm going to write the rule here. And we are using, as I'm explaining this, we are using this rule. So rule 2, from the book The Analysis, said the following. If the volume of y, y be made up of several terms, the area likewise shall be made up of the areas which result from every one of the terms. Okay. What this rule is saying is, again, something that you know. If you have, if you're talking about an integral of an expression that has many terms, then you can take the integral of each term, and that's exactly what I was saying here. Integral of 1 is x. I took integral of this, took integral of this, and integral of this. So I took the integral of each term. This is basically what rule number 2 is saying. So, so although the higher power of curves did not appear in the graph Newton actually constructed first, he went on to write down more area expressions for curves for this family, simply using rule 1 and 2. So let me write down some more before we interpolate them. or tabulate the results rather. So the area 1 plus x to the third is equal to area the area of 1 plus 3x plus 3x squared plus x to the 3. You might say, how do you know so quickly that this is what the expansion will look like? Remember we talked about the binomial theorem. If you actually use the binomial theorem to do 1 plus x to the third, you'll see that it comes down to that. But also, and I shall talk about it a little bit more, but probably in the other parts. At this time, Pascal's triangle was known. It was known by Newton as well. Pascal's triangle is a triangle, an infinite triangle of positive integer entries, and maybe I should just write it here. Pascal's triangle. So Pascal's triangle, let me just write down the first few terms and I'll tell you what the rule is if you haven't seen it before or if you don't remember. So you start with the tip of the triangle. It looks something like this. And so on. So those diagonals, or on the bottom of it, there is no bottom to this triangle, and it goes on to infinity. So although it seems like a very simple triangle to construct, but if you notice, the rule for each row is as follows. You keep adding the entries of the previous two diagonal entries for any entry. For example, so besides the first one that starts at 1, then you have 1 and 1 here. This 2 comes from adding 1 and 1. The two top entries on the top of 2. The 3 here comes from adding this 1 and this 2. The 3 here comes from adding this 2 and this 1. Then the next row, again you write 1, 1. Then the next entry will be 1 plus 2, 2 plus 1, 3 each time, and then 1. Here you have 4 comes from 1 plus 3, 6 comes from 3 plus 3, 4 comes from 3 plus 1, and then you write a 1 at the end, and so on. I mean, it's a fairly simple triangle, but it's extremely rich in properties, and that's the topic for another time. But also this time that we're talking about, it was known that the entries in any row of Pascal's triangle are the binomial coefficients, meaning are these entries here. For example, we are talking about 1 plus x to the power 3. 1 plus x to the power 3, so this is the 0th row, the first, the second row, the third row. So if you want to know what the expansion of something a plus b to the third looks like, it is telling you that these are the coefficients of that expansion. So that's why I wrote 1 plus 3x to the 1 plus 3x to the 2 plus x to the 3, and again it goes hand in hand with the actual binomial formula. So that's why I wrote what I wrote. And Now, if you take, by rule number 2, if you take the integral, or if you integrate each term here, we will have what? We will have from, this is all calculus 2 stuff. So that would be, again, integral of 1 is x. Then the next would be plus, you leave the 3 alone, integral of x is x to the 2 over 2. So 3x to the 2 over 2 plus 3x to the 3 over 3 plus x to the 4 over 4. Okay. What about the area under higher powers of 1 plus x? For example, x, 1 plus x to the 4. Okay. You can use Pascal's triangle to write down the coefficients, and then take the integral of each term like we did in the previous step. So it would be the area 1 plus 4x plus 6x to the power 2 plus 4x to the power 3 plus x to the power 4. And integrating each term, you will have again x plus 4x to the 2 over 2 plus 6x to the 3 over 3 plus 4x to the 4 over 4. I'm not cancelling out things here for a reason. Plus x to the 5 over 5. Okay, let me do one more. Then area under 1 plus x to the 5. Again, using the fifth row of Pascal's triangle, you can write it like we did before, just to save some space here. I am just going to write what the area is once you integrate each term in the expansion. So it is x plus 5x to the 2 over 2 plus 10x to the 3 over 3 plus 10x to the 4 over 4 plus 5x to the 5 over 5 plus x to the 6 over 6. Okay, so I repeat, he did not necessarily drew the graphs of all of this in the same picture and then used rule number 1 for looking at the areas under those curves. He's simply using pattern that we saw from the first few ones to actually tell what the area for these other curves would be. And then the next thing that he did, he tabulated the results, and he was looking, so tabulate the results. To come up with a general way of finding areas under the curve for the general curve 1 plus x to the power p in general, where p obviously would be so p is an integer power, positive or negative. Or negative. Okay. So before I tabulate the results, notice something. The denominators in the formulas of each of these areas. Okay. For example, the denominator in this formula is 1 and 2. The denominators in the next one are 1, 2, and 3. Denominators on the third one are 1, 2, 3, and 4. Denominators in the fourth one are 1, 2, 3, 4, and 5. And then 1, 2, 3, 4, 5, and 6. As you can see, the denominators for all of these areas or all of these terms are in arithmetic progression. For those of you who don't know what an arithmetic progression is, an arithmetic progression would be a sequence of numbers such that the difference between any two consecutive numbers is the same. In this case, the difference between any two consecutive numbers is 1, because you're going 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 6. So the denominators are all showing up as arithmetic progressions. What can you say about the numerators? The numerators for each area, the numerator here is 1, the numerator here is, well, the coefficients of the, when I mean the numerators as in coefficients of those terms, the numerator part. So here I have 1, here I have 1 and 1, here I have 1, I'm sorry, here I have 1, 2 and 1, here I have 1, 3, 3, 1, here I have 1, 4, 6, 4, 1, and here I have 1, 5, 10, 10, 5, 1. As you can see, the coefficients in the numerators for each term, for each of those areas, obey the Pascal's triangle. So now we are actually ready to tabulate the results, and I'm going to tabulate the results in the next page. Okay. So that is lecture 9, page 2, part 1. So we tabulate the results. So I make a table here. Alright, so bear with me. Okay, looking for my rulers. Okay, that's great. Okay, I got it. Alright, so let's see how many I want. I want 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. 2, 3, 4, 5, 6, 7, 8. Okay. Bear with me. Normally I would have prepared the grid before, but it's hard to tell at what point during the lecture I'll be finished with that first page. So I could not have prepared it in advance. Alright, so here are the results. So P here stands for, so here I'm going to write the powers that we're considering, and here down I'm going to write the term. All right, so let's say, well, he knew what 4 minus 2 minus 2, what minus 1 power looked like. He knew what power 0 looked like, areas under the curves that is, and their terms, power 2, power 3, 4, 5, and 6. And then he proceeded with the patterns that he has already for the known entries to find the areas under the curves. 1 plus x to the power minus 2, 1 plus x to the power minus 3, 1 plus x to the power minus 4. Okay, so let's see. Let's go to the first page. All right, for example, for 0, for power 0. For power 0, this is power, yes, so the line y equal to 1 is your power 0, which is just x. So here I'm going to write the coefficients x over 1, x to the, not coefficients, but the terms, what they should look like, x to the 2 over 2, x to the 3 over 3, x to the 4 over 4, x to the 5 over 5, x to the 6 over 6, x to the 7 over 7. Okay, so when we're considering 1 minus x to the power 0, area under that curve is just x. That means that I have, and the coefficient in front of that x is just 1. And I have no other terms, so other terms are non-existent for that power. All right, going to power 1. Area under 1 plus x to the power 1, as you can see from here, it is equal to x squared plus, I'm sorry, not x squared, x plus x squared over 2, x squared over 2. Okay, here the coefficient in front of x over 1 is 1, so I will also write 1. The coefficient in front of x to the 2 over 2 does appear in the formula for this area, and the coefficient in front of it is also 1. So here I'm going to fill this with coefficients in front of terms that look like this in the expansions of the form of the areas. Okay, so the rest of them are non-existent, so I'll just say 0. Area 1 plus x to the power 2 turns out to be x, 2x to the 2 over 2 plus x to the 3 over 3. I do have one term that looks like this, so coefficient in front of it is 1. Coefficient in front of the term x to the 2 over 2 is 2, so that's why I write here 2. Coefficient in front of x to the 3 over 3 is also 1, so I write 1. There are no coefficients of the form x to the 4 over 4, x to the 5 over 5, and so on, so I just write 0 for this. So area 1 plus x to the 3, looking at the formula, I have coefficient in front of the term x to be equal to 1. I have a term x to the 2 over 2, and the coefficient in front of it is 3. I have a term x, what am I saying? Yeah. I have a term x to the 3 over 3, and coefficient in front of it is 3, so I'll write 3 here. And I do have a term x to the 4 over 4, and the coefficient in front of it is 1. There are no more terms, so I just write 0. Moving on to the area 1 plus x to the power 4, I have all these terms here. So term x, coefficient 1. Term x to the 2 over 2 has coefficient 4, so I write 4. Term x to the 3 over 3 has coefficient 6, so I write 6. Term x to the 4 over 4 does appear, and it has the coefficient 4, so I write 4 here. And we have a term x to the 5 over 5 with coefficient 1, so I just write 1 here. There are no other terms. And the fifth, I also have the fifth. For the fifth, I have 1, I have 5, I have 10, I have 10, I have 5, I have 1, and I don't have something that says x to the 7 over 7. So as you can see from here, all the entries, as we mentioned before, look at this, all these entries actually obey Pascal's triangle on this part. And I know what the sixth one would look like. So this also should be 1. You see, you should have only ones and ones in both diagonals, and then you fill in the rest. So this next one would be the next one according to the Pascal's triangle. The next one would be 1 plus 5 or 6, 5 plus 10 or 15, 10 plus 10 or 20, 5 plus 10, 15, 6 and 1. Okay, well, the point is what to do with the negative powers. Well, let's see. I do have an expansion for well, that is the point actually. I don't know what the coefficients of 1 plus x to the minus 1 will look like, and that's what he was interested in. He wanted to know what the expansion of the area would look like formula wise, and he used the positive powers and the fact that all of these entries followed Pascal's triangle to actually fill in the rest of the table. Since that must be true, all of these entries actually have to be 1. All right, so this entry here, whatever it is, has to come from the sum of these two. From the sum, or rather, I'm sorry, this entry here, because I filled this part of the table. This entry here has to come from 1 plus whatever number that I have to put here. It's only one possibility for me to have a number here. It's minus 1, because 1 plus minus 1 gives me 0. Okay, now that I have this entry, I can complete this. To get a minus 1 here, what should I add to 1? I should add minus 2. To get minus 2 here, what should I add to 1 from here? I should have minus 3. And to get minus 3 here, I should add to 1 a minus 4. Okay? Well, for the next one, to get a 0 here, I should have a 1 here. To get a 1 here, what should I add to minus 2? I should add 3. Then here I should have a 6, and here I should have a 10. And knowing basically the rule, I can fill in the rest of the table. So I'm just going to fill in the rest of the table by the rule that I just mentioned. I also am going to write down the rule so you have it in your PDFs later on when you'll study. All right, so 35, 15. You should check that everything works. Minus 56, minus 21, minus 6, minus 1, and then 84, 28, 7, and 1. What does that mean? It means that, so this means that the expansion of area under the curve 1 over 1 plus x, what area was this? This was the power minus 1 basically. That's the power minus 1 that we're looking for, which is area under y equals to 1 plus x. That is 1 plus x to the power minus 1. It will have so far those 7 terms, and the coefficients of each term will be 1 minus 1, 1 minus 1, and so on. The terms will look like this. This is what the table is saying. So you will have 1 times x, okay, minus x to the 2 over 2 plus x to the 3 over 3 minus x to the 4 over 4 plus x to the 5 over 5 minus x to the 6 over 6 plus x to the 7 over 7. Of course, it doesn't stop here. This is an approximation. The more terms you have, the better approximation of the area you have. So you can continue with this table indefinitely. As you probably remember from Calculus 2, we're talking about close approximations of the areas. And then we take the limits and so on. Okay, so he could tell more or less for a bunch of terms or as many terms as he wanted what the expansion or what the formula for the area under the curve 1 plus x to the power minus 1 looked like. So again here the rule is each entry is the sum of the entry to the left of it, and above that are above that one, not that's to above one, that is obviously on the left. That's what you do. Okay, so that's basically the rule. I'm going to stop here for part 1 and I'll continue with part 2 in a minute.